I think actually one of the most important computational feature of biological networks of neurons is that they learn then. And I think possibly one should first think about their learning and then computation follows from this. So this is just one suggestion. So I want to talk today about principles for learning. And we all know how useful backprop has been. And on a very abstract level, backprop relates a global optimization goal, namely gradient descent in some error landscape with local learning rules. And this is something we don't have so often in network of spiking neurons. And you all know if you just release SDP in some recurrent networks, all kinds of things go on, but rarely something that you really want to see them. And so therefore, I want to propose here today two principles which in principle have the capability to relate global network properties to local plasticity rules like SDP, but actually also they relate to other types of plasticity. So Jeff Hopkins and Narayan Srinivasa talked about spine dynamics, network rewiring, and I think it's also necessary to integrate these features into a more principled framework. And then also in the end, I think we should really also approach the perspective of network optimization. There are powerful optimization methods, non-linear optimization methods. Simulated annealing is one of them. It was already mentioned. And I think it would be very nice to see that network learning can be viewed or can recruit the power of global network optimization. So very concretely, and I want to sketch two principles. One is expectation maximization, EM. Another one now related to making use of Fokker-Planck equation. So both of these principles are actually very old principles. I think it's maybe they have not been considered much in the context of spiking networks. So let me first talk about expectation maximization. And so this builds on work which has been published a few years ago, Bernhard Nessler et al. And Habenschuss et al. And this one feature of this first principle, EM, is that you can't apply it, as far as I can see, to an arbitrary architecture. It needs to have a particular architecture to work well. And the architecture here that I'm considering, Giacomo had already talked about this kind of probabilistic or soft winner-take-all circuits. This is one architecture where this particular method works particularly well. It requires to have stochastic neurons where the firing probability is really essential, and it results through a simple exponential formula from the membrane potential. And here I consider here only plasticity applied to these synapses from the external high-dimensional spike inputs streams to competing neurons. And each of these neurons, they compete to become an expert for the current pattern which is there in the input there. And what is nice is that one can see this network of spiking neurons as a concrete emulation of EM that tries on an abstract level to fit a mixer distribution to the distribution of inputs as they come in here. And so therefore one sees then actually that each of these competing neurons can then be related on this more abstract level to one component of this mixer distribution. And by modulating the concrete shape of the SDP rule, this was shown particularly in this Habenschuss paper, one can modulate also so that in principle any mixture of exponential family distributions fitted to this input. And so this I think is quite nice because you have all the zillions of synapses. They're just applying SDP, they have no idea what's going on, but having this plasticity rules in this concrete architecture tells us that something much more powerful can happen there. And I think you're all familiar with expectation maximization. It's a very old method. And as you know, probably the majority of unsupervised learning methods in machine learning use EM one way or another. What is nice is here, usually EM requires really a supervisor which says now we have an E phase and now we have an M phase. In this case, the E step is simply, you have a competition and one of the neuron fires at the moment, and this is the E step. In the M step, that neuron that has fired can apply SDP. As you know, SDP requires pre- and postsynaptic activity, so only the winner neuron can apply SDP then. And you simply apply it there in this continuous time, and this is then, you can interpret this as an M step. Then the next patterns come in then, they're coming continuously. You have another winner, which is the winning kind of bias has been somewhat changed through the previous M step, and then you repeat this then. And the nice aspect of EM is that in principle it tells you that this process is not running around in circles, but there's something optimized in the background then. And this is in the end the first approximation, the KL divergence, but more concretely a bound for the KL divergence is really brought to some minimum then. And so this is just this fitting of this internal model, this mixture model, to the external input stream. There's also very nice work by David Kappel, published last year, that in principle you can also apply this to HMM learning. So Jeff Hawkins talked about this goal of really learning sequences, predicting sequences, and this can be emulated here. The only thing that you have to add is here synaptic connections among these competing neurons and apply the same SDP rule to all of them, and then you even have a theoretical guarantee that in principle it fits HMM's hidden Markov models to this sequence of input streams. So to make this run optimally, you need to have also a particular tuned SDP rules, and then one can understand this, that this SDP rule really, the equilibrium of a weight can be interpreted in log condition probabilities, namely condition on that the postsynaptic neuron fires at some time t, that the presynaptic neuron has fired just before. So this is just technique. So this is the main tool to relate this to this theory. So, but in principle, I think it's what is nice about this theoretical approach is, and this is something I think one has to look for in neuromorphic engineering, that the theory provides a gold standard. This tells you under ideal conditions, this theory takes place then with this guarantee then. So in real world, you are not able always to satisfy this gold standard, but at least you know what would be optimal. And I think this is really an advantage, compared with just trying out various options then. So I want to briefly only sketch on 2 slides one more recent application. So this is a paper, I just put it on my webpage this week then with Diane Pekevsky, where we have used this principle, but now we see then that if you put many of these models together, you get a much more powerful learning device, a little bit in the spirit of Giacomo, of connecting now many winner-take-all-like circuits. And here the setup is the following. We're having something rather ambitious goal. You assume now you have an external input stream. It has an unknown distribution P star. It's a high-dimensional inputs, and this can be spikes or anything else, but it's really geared for spikes here. And so all these samples are coming now in, maybe a time window where some neurons are spiking and not then. And the goal of this should then be to build an internal model for this external distribution P star then. And the only constraint, a priori, for this P star, it should be a distribution over discrete variables, binary or multinomial variables. And I think it's an interesting open problem, maybe for you to work on how to extend this also to continuous valued variables then. But anyway, so this builds an internal model for this. And so this is automatic and autonomous. So if, for example, P star changes, automatically this internal model will adjust then. And the principle for this is actually quite simple. So for each of the components here, say this is the variable yk, so from the nth example here that it's getting, this is the component yk, so this is one random variable together with the values of some other variables. Ideally, you want to have here the Markov blanket. So some of these variables which have the property that this variable conditioned on the values of these becomes independent of the remaining variables. And so this is now a certain subset of these components from each example, and they're led to a particular unit which processes this, and this unit has a very concrete goal. This kth unit, namely, it's supposed to learn the condition probability table for this kth random variable, depending on the other variables in the Markov blanket there. And it turns out that for learning this condition probability table, you can use something, a learning module, which is very similar to this winner-take-all circuit that I have shown. So this part here is basically a winner-take-all circuit of the same type I've shown before. But it's now simply a little bit different because you have here now this variable yk then, in this case 1, which may have here in this case assume 2 value. And so but in principle what you're doing is here for the case that this variable assumes the value 1, you want to build, now what are the typical scenarios of these variables in the Markov blanket when this variable wants to be 1 then. So build an internal model for this probability table. What's also interesting is here that now if you want to fully learn this, now ideally you possibly need here a huge number of hidden neurons there. In the worst case, exponentially in the size of the Markov blanket. But we have the impression one typically also gets something reasonable out there if you simply have here smaller numbers. You simply approximate this extremely complicated mixture of multinomial distribution here by some simpler mixture which has simply fewer terms then. And it depends, of course, on the data, how many you want to have it or need in this mixture. You could even think about adaptive process when you think this is not working well, that you add some hidden neurons to increase this expressive capability. So in principle, this is something which combines aspects of parameter learning of Bayesian networks together with structure learning, but in a somewhat more kind of hardware closer approach towards structure learning then. And so therefore also for this, there's a theoretical guarantee. So in this paper we have applied it to a relatively simple example, which is more kind of discussed in the context of cognitive science. There's this Knille and Kersten old paper which showed that not just for visual perception, that some probabilistic inference takes place in our brain. Then you can model this with 4 random variables. And it has this explaining away effect, so therefore it's a non-trivial one, so it has higher order terms. And so this is therefore a good test case because this theoretical approach is not constrained that this P star has only lower order terms. You can have arbitrary high order terms, and in particular it can do explaining away then. So the method of going from this Bayesian network to this network now of neurons is you have now 4 learning modules. Each of these learning modules looks like the one that I've shown you, which has as its heart winner-take-all-like circuits. They're all kind of continuously firing. There's no overhead control or timing or clock or so necessary. But still, from this theory of M, we guaranteed that each of these modules builds an internal model for the probability table. And so these are these Kullback-Leibler divergences for those 4 modules. And you see like this green models doesn't really hit 0. So there are no kind of approximations then, and we probably didn't use the right number of neurons here, or large enough neurons. But anyway, we see pretty soon all these scale divergences become pretty small then. And so this, I think, is something which is nice. We saw, although it's a very complex networks, because we have some theoretical understanding, it improves then over time. And so this is, after a while here then, comparing now the statistics, simply the internal model for P star, which is green, with the ground truth, this unknown P star, and you see for each of these kind of joint assignments to these 4 binary variables here, it produces a pretty good internal model then. And so this is something which is nice, and I think it would be nice also to see this in neuromorphic hardware implemented, because you simply can set it outside, point it at the world, and automatically builds a model of the statistics of the inputs that have come recently into this network there. So now I want to talk about the second topic, which is of a different nature. It uses different principles, and it's not really constrained to any particular type of network. It doesn't even have to be a spiking network, and also it's very general with regard to the plasticity rule. So in principles, you can apply it to any type of local plasticity rule. The only constraint that is needed there is actually an unusual one, because you see in a moment then you need to add one stochastic component to the plasticity rule, which is one which you usually don't do there. So in that sense, a little bit unusual. But one motivation for this is this continuous spine dynamics and rewiring that you have seen then. So this is a very nice paper from the Simon Rumpel lab from last year, Löwenstein et al. In PNAS. And so this shows here from one session, the new spines that they observed here, how many of them survived then. So you see here after 8 days, most of them are gone. You're here at 20%. And so this is overall the statistics. So when today you know which synaptic connections are there, so after how many here, 5 days or so, half of them are lost then. And so this is the adult mouse cortex there. And the argument of the researcher is that this happens all the time, also in our brains, adult brains, that it's not something specific for development, and there are probably processes that regulate the speed of this. But I find it quite surprising now that we have stable function in spite of the network all the time changing under our feet then. And for me, one motivation was really to get a theoretical handle on this situation that stable network function, stable learning could be in principle possible in spite of the fact that all the time things change under your feet then. So this is now newer work then, so it was last year published. David Kappel is a great PhD student, Robert Legenstein, associate professor in our lab, and Stefan Habenschoss was a postdoc. He's now working in industry, and they are the authors on this paper. So I told you, there's one new term in this plasticity rule. So all plasticity rules that I'm discussing here now from now on will have this form here. So they in principle, technically, these are stochastic differential equation. So the new term is this term here, where this dW is a step of a random walk closer, more precisely, an infinitesimal step of a random walk. So just it goes up and down then, and it, like a random walk, it can wander a little bit away or so from zero in some direction. And so then you have here some B then, which is just a learning rate. You can modulate, it regulates simply the time scale. This is T is an interesting parameter because you see it only scales this noise term here on this plasticity term, and I will come back to this on the last slide. Until that, I will now always assume T is equal 1. I don't want to deal with this. So now let's look at this term. So this is the term where what you usually have then, like an STP rule, would be part of this then. And an interesting aspect is that the way how this rule is written here, it relates right away this local plasticity rule, which just cares about one parameter, theta I, out of millions of parameters possibly, in terms of a certain target function. So P star is now something completely different. P star is a kind of desirable distribution of a network configuration. Think now this, you have a million parameters, theta, and they really determine the current network configuration, both which connections are currently active, what is the weight of the synaptic connections, but also excitability of neurons, delays, whatever. And the P star is now really the target. So this is a little bit an analogy to when you do backprop, you have a certain kind of target function that you want to modulate. Here, we are not talking about supervised learning, but unsupervised learning, remote-based learning, as you see in a moment. But anyway, this is here a target function. So I think maybe the most powerful kind of special case is the case of reinforcement learning, where simply you want to have that the network configurations theta, which get the highest rewards typically, they should have the largest mass under this distribution. When you're learning, you have no idea what this P star is, then nobody really knows it, right? And so what we want to see that nevertheless, this network kind of moves towards this distribution, so that most of the time the network configuration will approach this one, so that most of the time it has high value, it produces then high rewards then. So more technically, you see you have a log here, which we find in a moment very useful in case this is a product, and then you simply have the partial derivative then. And the success of this theory-driven learning approach depends on how well you can now approximate with a local learning rule like SCDB or kind of spine dynamics, this partial derivative then. So at least from biological perspective, you have bad luck. This may be a non-local learning rule, right? If you have a non-neuromorphic device, this may not be fatal, but you still care about what variables this depends on. So typically this game amounts you have a certain well-defined learning target. Now, how well can you implement in your neuromorphic device this drift term here then? So altogether, the theory which tells us that we simply let this run for each parameter in parallel, and that the station distribution of this resulting Markov chain on the parameter level will have a station distribution p star of theta. Well, assume at the moment t is equal 1 then. And so the Markov Blanket equation tells you also exactly when you started from the initial state and you have it run until time t, what is now the current distribution. And so in the end, I think it is, of course, very important not just to know what the station distribution is, but where you are after you have started, you have run a finite time from a given initial state. So I will ignore all this question, but I think this will be the question which arises necessarily when one now takes this approach and would apply it to some concrete neuromorphic device. You really have to care about the convergence of this learning. Now, in this case, how fast you are converged to the stationary distribution then. And you see, I think one important difference is I don't talk about convergence to a particular value of theta, right? No, it's not convergent to a learning result, but converging to a distribution of network parameters, right? And so therefore, you have to assume this network will never stop learning then, right? It's continuous learning there. And you may even, this is, I think, interesting, you may change p star then, right? Or something changes in the network. It will still follow the same rule. It will always try to track, what is the current p star then. And so we coined the term synaptic sampling for this because these are the parameters which regulate one synaptic weight plus its connectivity, as opposed to neural sampling, which is more stochasticity on the level of activity with fixed theta. So in principle now, the theoretical approach can be applied to basically any concrete learning approach then. I will briefly discuss here the case of unsupervised learning. We have a generative model. And so in common of both of the approaches, which I will briefly discuss, is that you can bring in our prior. And so this is good. I think in most neuromorphic cases, you actually want to have a prior, because even if the network for some way decides it wants to have everybody connected to every neuron, you don't want to have this, right? You can't handle this well. So you have a certain sparsity prior as a minimum, right? And so this is now a systematic way of scaling into this general approach any prior actually that you want to. So in this case, of generative model, we assume X is now an example of repeatedly occurring inputs, say a set of visual patterns of images, and we now want to that the network builds an internal model for these visual inputs there, so that theta is optimized in such a way that the probability, the likelihood of this ensemble of inputs is maximized. But it's also that altogether this p star is influenced by the prior according to this then. So therefore now, if one wants to apply this now, you need to have a generative model, and then you have to talk about a more specific model then. So this approach was published last year. So in the works now is work on this reinforcement learning approach, which I think has in principle more potential, but is much more generally applicable because it doesn't require that you have a particular generative model running on your neuromorphic hardware. If you can just tell occasionally the network when you are happy with what it's doing or whether it has made progress there. So this is the only information it needs, but then you can apply it in principle to any recurrent network. And you see here, instead of having here being able to create a likelihood for this high likelihood for the actually occurring data, you simply want to have theta, which maximizes the probability of rewards. Then this is what you need here then. And so this is something where we need a few more months to work this out. We're starting this now. Actually, there's a lot of information about also rewiring, reward-based rewiring in biology. And we will see here then that when we look at these concrete partial derivatives, one gets also back from the general principles rules for third factor based learning rules which were proposed on different grounds previously. So let me just quickly tell you also simple analytical way how one can combine network rewiring. Jeff Hawkins had shown a very similar picture. So as you know, these dendrites, this spines here are kind of shrinking and expanding, then occasionally they form a connection, and once the connection is there, then you can talk about synaptic plasticity, where the weight gets larger, which causes then also typically larger spine volumes. But you have here a phase where this dendrite, the spine here doesn't know about the presynaptic activity, so you can't apply SDP here in this context. And so therefore, the learning rules look like this, that in this case, you only have this here, this random walk, basically. And it turns out, together with here, if you use as a prior here, Gaussian, then these two terms together then reproduce an Ornstein-Uhlenbeck process for this case of spine dynamics before they have made a connection then. And so this appears to fit biological data quite well then. And then if you take a closer look at how we relate synaptic weight to this theta I, so the idea is whenever theta is larger than 0, then it's really now an existing synapse, and then we use this formula that Wi depends exponentially on the theta I minus theta 0, so we have just here, we want to have that this curve here starts here at theta equals 0, so therefore we typically subtract here number 3 or something like this, and to make this curve here only take off, so that only after you have an existing connection, which is here this white area, then you can talk about the weight then. And it turns out that if you simply take now this partial derivative in terms of P star then that I had mentioned, then you have here this term here which arises from the prior, and you have now this term here where you have here this factor then, which is basically non-zero only if you have a kind of functional synaptic connection, and then you have this term which is now again more term in terms of the usual type rule, and so this amounts to a version of SDP if you apply it to concrete model then. So therefore this is just one quick look at how you in principle can combine this more abstract framework and arrive in the end at SDP rules, but also you can integrate synapse dynamics, at least in a biologically quite realistic way according to the data that one has so far. So therefore, so far there are many models for spine dynamics and also for synaptic plasticity, but I think already several of the previous speakers suggested we should integrate both, and so this is one simple rule of doing this. I quickly want to demonstrate also in 2 minutes, but only very fast then, that one implicit and automatic advantage of this approach here for learning through the synaptic sample is automatic self-repair. And so we here have here in the paper, maybe if you want to read it up, we have here a situation of sensory integration of some visual input and spoken input, both are digit, and so this is now emulating an auditory cortex piece and here a visual cortex piece. And now we subject both the connections from this input arrays to this cortex arrays and the ones between these two cortex arrays, all to this rule which I have sketched on the previous slide then. And then we see here that, for example, here, this is now the situation of a network where it has seen for a while both spoken ones and visual ones and spoken ones and MNIST ones. Then it has formed a number of connections, which are the associations between them. And we measure performance by then only giving a spoken digit and then seeing how well this kind of the weights, the activated neurons in the visual cortex produce an internal model for the visual representation of the figure, which is shown up here then. And so, for example, in the first lesion, so this is now measuring performance here in this kind of reconstruction of the visual input in this generative model. And so here we have been very mean. We have removed now from this visual cortex all neurons which have been encoding a 2. So this neuron has been encoding a 2. So we removed it here. This one has been removed. So in principle, it's not just a random crippling of the network. It's a mean crippling of the network. We have removed all representations on the visual cortex for the letter 1 then. And so then we let it simply the network doesn't get told to do something different, it just keeps running, and it, again then after a while it has no established connection, and it has reassigned this remaining neurons, some of them represent 2s and some of them 1. So we have another lesion which is here even meaner. We have removed now all connections between these two kind of cortices, so then after a while, it still recovers, then it grows some back then and gets close to performance. And I think that altogether the picture which is maybe best conveys the ideas is here we check kind of in the three principal components, this vector theta, and we see here in this phase when it's just learning, it's cruising around in this space. When you make a lesion, nothing so drastically happens. You kind of you nudge the network to search now in a somewhat different part because you have essentially changed P star at this point, right? And here when you make another lesion, again, you nudge the network now to kind of sample from a different P star then, which reflects the second lesion then. So this is something which we can expect here. I want to quickly move to then the reinforcement learning slide. So this is my last slide before the summary. And one thing that I like very much about this approach of reinforcement learning is that in principle it has the theoretical promise of applying of recruiting the full power of simulated annealing for optimizing network so that it gets maximum reward then. And so this is very nice because we are used to being stuck in local minima, particularly also in reinforcement learning. And here what's of course essential is that we need to have now a cooling schedule then, because it's essential whenever you have now the particular value of t, that this parameter theta moves really to the stationary distribution, which is the right one for this particular value of t then. And so therefore this becomes now a new kind of engineering discipline, possibly to really have now fast sampling in this parameter space theta, insofar that you want to have fast, within a few steps you want to move to the stationary distribution. But then the theoretical guarantee tells you that in principle now, if you have the right cooling schedule, you can really reach the global optimum of a network configuration where you're then only staying at a very small part of this parameter space where you get maximal reward then. And so therefore, this is something which I think we should think about. We should be less modest with network learning. We should really try not to do global optimization, really optimal, not global optimum, not local optimum with network learning then. So I've discussed these two principles, which have somewhat different pros and cons. The simpler one with EM, as I mentioned, there the gold standard is you want to have particular kind of network modules and also particular learning rules, but then it can recruit EM then, which is nice. And the second approach is much more general, and we're just actually starting now to work on this. I think there are many more issues which have to be explored. But also the second one provides you gold standards, because now you have a way of judging the quality of local learning rules from the perspective, how well do they approximate this partial derivative from the P star, and you actually have to reflect what is actually your P star, what is your ideal distribution of parameter vectors there. And I think hopefully this provides some new ideas for our work then. Thank you for your attention.
So we have time for a quick question while next speaker gets set up. So one quick question I have, Wolfgang, is so you have so everything about me is neurogenesis. So neurogenesis would fit under your model as well. We could add new neurons. So you have a synaptogenesis model.
Sorry, didn't I catch the first part?
So I study a neurogenesis where you're adding new neurons into a network. That would fit under your model as well.
Right. You would have to work on it somewhat, right? You need somehow have kind of virtual holes where later neuron could come and go then. But it hopefully at least would provide you again some principles for neurogenesis. Yeah, this is a good point then, yeah.